Hey everybody, this is Dr. Walker here. This is video 222. It's called Capacitors with Dielectrics. A dielectric material is an insulating material, so an insulator, that increases the capacitance of your capacitor. So examples are rubber, plastic, wax paper. All you do is you place that dielectric in between the plates of the capacitor, and it now has a bigger capacitance without having to increase the area of the plates or decrease the distance between the plates. So how does it work? Let's look at the atomic description. I like going over this because it's a good refresher of topics that we've talked about. So this insulating material in between the two plates of the capacitor here, it becomes polarized. We learned that in an insulator we have the separation of charges within the atoms, but you still have a net overall negative charge on the left and a net overall positive charge on the right. So in your capacitor, so I wrote disconnected, so what I mean here, it has been charged, but it's not connected to the battery anymore, but it's just storing that charge. So your positive plates being on the left and your negative plates being on the right created an electric field pointing to the right. But what happened now that it has been polarized, you now have an electric field that is produced that goes to the left because you have a net positive charge on the right and a net negative charge on the left. So this reduces the overall electric field. You have the old electric field to the right, the new electric field to the left. Overall, you have less electric field. Since the distance between the plates hasn't changed, if you remember this equation that the potential difference equals negative ED, well, if you don't change the distance, but if you decrease the electric field, then you're also decreasing the potential difference. So again, this is why I was talking about a disconnected capacitor, because if it was connected, then we wouldn't be able to go through this analysis because the potential difference would stay the same. So the potential difference is reduced across this capacitor just by placing the dielectric, and as a result, the capacitance increases. So how do we know this? Well, the equation for capacitance is capacitance equals charge per potential difference. And when your capacitor has been disconnected, then the charges cannot move around. The positive charges are staying on this plate on the left here. They have nowhere to go. It's not connected. So if charge stays constant and potential difference is reduced, then that means that capacitance increases. So this did take a few steps, but it's just good to be able to go through this kind of process of putting different topics together to analyze situations. So simply putting this insulator within your capacitor is going to increase its capacitance. The equation for this is basically that now if there is a dielectric in our capacitor, then to find the capacitance of that capacitor, we use the old equation, which is epsilon times A over D, but we multiply that old capacitance by the dielectric constant kappa. So basically, if a material has a constant of 3, well, then its capacitance is 3 times greater than if that constant wasn't there. So the constant is determining the factor by which the capacitance is increased. It will be simple plug-and-check problems when we do have dielectrics, so we will do one of those in the practice problems, but for most of this chapter we will deal with capacitors without dielectrics, but they are often used, so it was definitely a good idea to mention them. Let's do a quick question here. Placing a dielectric between the plates of a capacitor, what does it do? Alright, you've got it. So it's going to increase the capacitance. This was just a very quick review question about what we just talked about. And the last thing that I wanted to talk about, I thought was very interesting, is called dielectric strength. So it's not the same thing as dielectric material. does have the same word, but dielectric strength of something is referring to actually to an electric field. So the maximum electric field that will break down a material. So for air, the dielectric strength is around 3 × 10⁶. Volts per meter is also a unit for electric field. So newtons per coulomb, volts per meter, those units are equivalent. So what this means is that if you have just plain regular air and the electric field is at least this high, then the electric field will start to break down the air, ionize the air. And we talked about in a previous video that this is when lightning can start occurring, when the air has been ionized and there's a pathway for the charges to flow. So the same thing happens in a capacitor. If you don't have a dielectric and you have a capacitor, well, you might think, well, if increasing the voltage, then that increases the charge on the plates. Why don't we just have a very high voltage on those capacitors? Well, if the voltage gets too high, then the electric field gets too high. It's going to break down the air here, and the charges will start flowing, and you won't have, your capacitor will be discharged. It won't be able to store any charge. When you have a dielectric within your capacitor, then now you're going to need a stronger electric field to break it down. So it will allow you to put a higher voltage to that capacitor, and so it will be able to store more charge. Alright, that's it for this video. The next video will be about how much energy is stored in our capacitors. Remember, that's the whole point of capacitors. Store energy and also release that energy. See you soon.